I will say, for the reasons of time, this session assumes that you understand basic Python syntax. There's little new bits that we'll encounter here and there that I'll explain as we go along, but if you really are uncomfortable with Python, I won't be going through Python for, if you know nothing about it at all. So just as a disclaimer, but hopefully, if you've got a bit of a grasp, you'll be fine. Actually, before I start, I do need to point out that a lot of the code examples in these slides are adapted from pythonprogramming.net, which is an amazing resource, yes, they do some fantastic things over there, so I would encourage you to go and check out that website if you're interested in learning more about Python, like advanced topics and things like that. He does a really good NLTK tutorial, which bits of this are kind of adapted from, so thank you very much to him. So what is NLP? So NLP, or natural language processing, is basically how we take computers and we get them to understand natural languages. So computers are very computers are programmed, so computers understand some form of language. It's just not a natural language with all these wonderful kind of quirks we have of English and Japanese, Chinese, all sorts of different languages. Every natural language, I just realised that's still on, every natural language has some weirdness to it, and computers have some issues understanding a bit of weirdness. Computers like things that are very discrete. They like, here is a number, it is a number, that's it. Or if this thing is this, then do this. They like things that are very easy to predict, very deterministic. So when you give them a natural language and you give them a sentence that can have 5 different meanings depending on how you say it, where the punctuation is, like how aggressively you say it, whether there's a question mark at the end, like all of these different things, they kind of freak out a little bit. But as you've probably seen, if you have an iPhone or an Android phone or any kind of phone nowadays, most phones come with a voice assistant, which is able to understand basic natural language that you speak to it, and it can interpret that as commands. There are issues with natural language, and that's where a lot of the interesting research is right now. So as I've said, natural language is inherently quite ambiguous sometimes, which can cause problems. So if you say delete this thing, what are you referring to? Say you've moved into a folder and you've selected a file, or you've selected multiple files, and you say delete this thing. Is it the thing your cursor's underneath? Is it everything in the folder? Is it, there's lots of weird ambiguity with natural language, which can cause issues with certain things, especially when we get into the realms of telling computers what to do. There is a reason why programming languages don't read like natural languages. They've got similarities, but they don't read like English, for example, and that's because computers need a kind of defined set syntax. You don't really get that with natural language. So I'm going to exit out of this for a little bit and just introduce natural language processing. Actually, before I do that, I do apologize. I'm going to just talk you through how to set up NLTK. So so you can kind of struggle with this while I'm talking about everything else. So there's a couple of things you need to install. So if you're on Windows, the thing at the top is what you need to do. You need to go to python.org and then go to downloads, and there should be a download for Windows. You can run through the installer and install Python. If you're on Linux, then that top command up there will work for Ubuntu, but I'm assuming if you're on Linux, you either already have Python installed or know how to do it. So I'm being very generous by giving that. But yeah, if you're on Ubuntu Linux, that will work. If you're on anything else, then figure it out yourself. If you have a Mac, then open a terminal, and you should already have Python available. You may need to do a bit of Googling, because I think some Macs you have to enable developer options or something like that. But yeah, if you go to python.org for any operating system, it should help you to install things. It will give you better guides than I can. So you need to install Python, and you need to install pip. So we talked briefly at the end of the last session about pip, which is the Python package manager. So a lot of programming languages nowadays don't only just ship with an interpreter or a compiler, which turns your code that you've written into code that the computer understands. They also ship with package managers and some other cool tools that are quite useful. So pip allows us to install modules that are created by other people. I think, did we talk about modules? I think we briefly talked about modules. So just to have a little bit of a recap, I've got some better slides now that I've actually had some time to look at them and edit them. You can basically write code in another file and then bring it into your file. So this file is called stuff.py, because I'm very good at naming things. We've got define say hello, so we've got a function declaration. It takes an argument thing and then just says hello to whatever that thing is. Then main.py imports this stuff, and you just say stuff.sayhello and stuff.sayhello. So we can call that function from this separate file. So these two would be two separate files here. This, we're assuming, is some directory, and they're both in the same folder. They're both in the same directory. And we can also do an alternative little syntax. So if we don't want to do this stuff dot all the time, we can do from stuff import say hello, and then just call say hello, if that makes sense. Basically, the fundamental principle is that you can grab stuff from other people's code and use it in your code. You can essentially just put an entire other person's file and grab everything out of it in Python. There isn't a lot of restriction, which is great for you, bad for if they want to hide anything from you, which in some cases that may be what the programmer developing the library wants to do. But every language has its imperfections. So there's another longer example here for generating random numbers and doing like a spinning game, but we won't get into that. Fundamentally, you just need to know that you can import other people's code. Pip is a way that we get that code. So you can go to, I'm just trying to think of Python libraries I know of. So you can basically Google a Python library and you'll get a page that looks like this. And it will say pip install pyyaml. This is the command to install this package. Don't need to worry about what it does. Just essentially, this is how you install packages into Python. And this allows you to then use someone else's code. So in this case, YAML is like a language which we use to store data. So this would allow you to read YAML files. We're not going to get into YAML, so don't worry about that. But yeah, the fundamental principle is you can come in here and kind of search for a load of cool stuff in this index. There's loads of different projects that other people have worked on because, so for instance, if you want to develop web applications, Flask makes that really easy. So once you've installed it, it makes it a lot easier to develop web apps in Python. So there's lots of different modules. You can go and grab them, download them, and play about with them. So that's one of the reasons Python is really cool, because it has lots of cool modules that we can install and mess about with. So just going back to this, I'll talk about that in a little bit. This is the main thing you need to do to install NLTK. So to actually install NLTK, it's the top black box. So go to nltk.org. This NLTK stands for the Natural Language Processing Toolkit. And it's basically or I think it is just Natural Language Toolkit. It's basically a library that we're going to use in Python that has a load of really, really cool stuff that we can use for natural language processing. So we're going to get into doing a little bit of basic natural language processing and learn some basic concepts in a little bit. I've got install instructions for Windows and for Mac and Linux. So once you've installed Python and once you've installed pip, with Windows you can run that command. If you run any command line, if you just go to the little search box in your Windows thing and search for CMD and just press enter, it will open up the first result and you can run that command in there. You can also run Python scripts from a terminal like that. In Mac and Linux, you can do lines 7 and 8 on this little thing, depending on whether you've got pip or pip3. I think this one is Linux and this one is Mac on the top, generally, but they're a little bit weird. If you have any issues, there's not a whole lot of time I'm going to have to debug things, but by all means pop down at the end and I'll help you out. Hopefully you'll be able to follow without actually giving it a go yourself, and these slides will be made available, so if you want to steal the code off them, as you can see, you can just click copy, and it's really easy to just play about with these code samples. Okay, once you've installed NLTK, you can import it just with import NLTK, just like that example file, and then you just need to do nltk.download, which downloads all the corpora that come with NLTK. So not only is NLTK a really, really cool tool for doing natural language processing, it's also a really cool tool to start natural language processing, because one of the biggest concerns in the AI world and in the natural language processing world, the data science world, is getting data. Data is pretty important. So in our case, we should probably get some language to process. I think that'd be pretty good. So NLTK provides all these corpora, which have tons of cool little things that we can mess about with. I think they've got like Brown versus the Board of Education. They've got the King James Bible. They've got they've got, I think, all the State of the Union addresses, so we'll be looking at one of those. So there's tons of stuff to play about with. I definitely haven't discovered all of it. But basically, if you just click on this download button, so when you run this code, this little window will pop up, and you just click download, and it will download everything. So you just need everything, unfortunately. So I hope you've got some space on your computer. I think it takes about 1 gig or 2 gigs of space. It's a lot of text. Hopefully, that's okay. We'll come back to that. I'm just going to do a bit of a brief introduction to natural language processing in general. So I'm stealing this with permission, of course, from, oh, fantastic. I'm stealing this from Dr. Paul Rayson, who couldn't join us tonight. Paul is a reader in natural language processing in our department, and he, at one point, delivered SEC 361, which is our artificial intelligence module. This is a third-year module. Don't worry, I'm not going to be teaching you third-year computer science, so please, if that scares you, don't run away. I'm just going to be going through the kind of basics of natural language. To be honest, this would be very difficult for computer science students, but if you're linguistics students, there will be a lot in this where you kind of go, hey, I was taught that in first year, so I'm going to skip over a lot of this. There's 70 slides here, but there's no way we're going through all of them like really slowly. So basically, there's a really cool book for NLP there. There's the Stanford book is really good. Also NLTK, the actual documentation for NLTK is as good as for just learning natural language processing. So that's dead good. But Stanford has some really good stuff. We have some really interesting natural language research that has gone on at Lancaster, and that still goes on at Lancaster. We're home to the UCRL Natural Language Processing Institute, which is cross-discipline, so we are quite relevant in that world, which is quite cool. Paul himself actually edits a frequency dictionary for natural languages, so he's the series editor for a frequency dictionary for Portuguese and Spanish and English and lots of different natural languages, where it basically lists all the words by how much they're used. So apparently the English one is his most cited publication, and it's essentially a book with a massive list in. So yeah, if you like reading a massive list for over 600 pages, I think there's about 100,000 words in, something like that. They basically like got everything that is used more than like 1 to 5% of the time by people. So it's a pretty long list. I wouldn't recommend reading it from top to bottom, but you know, if that's your kind of thing, Google him, search him on Amazon. So yeah, as I've said, by natural languages, we mean English, Russian, Finnish, Arabic, rather than machine-readable languages. So the difference being is that machine-readable languages are designed to be an abstraction on top of binary, on top of machine code, which allow a compiler to translate higher-level, abstract, easier-to-understand code, like Python, for instance, into machine-readable instructions. Because, like I said last time, if we're all writing in binary, our code's going to look horrible, and no one's going to want to program in it, and no one's going to know how to program in it. Just don't do that. So on top of binary, I think I said this last time, top of binary, we have these machine instructions, which basically map on one-to-one to binary. And then, so that makes it slightly easier to write, but then these machine instructions are really hard themselves to write. So on top of that, we have an abstraction, which is when we have languages like C, and C will then get run through a compiler, and that will produce this binary machine code that the computer can interpret. Programming languages have a strict alphabet, a strict kind of, well, not a strict alphabet, they have a strict syntax and a strict structure. So a compiler not only will just go, oh, here's some code, compile it, it will also throw you some errors and warnings. So if your code is garbage, it will tell you and kind of go, no, I'm not compiling that, that won't work. There are things that it will miss because there are things that you can't check for. So for example, and I'm getting a little bit off topic, but there is a problem in computer science called the halting problem, which is unsolvable. So you can't determine whether a program given a certain set of inputs will halt. It's impossible to work out that problem. So essentially, if you've written some code that will loop indefinitely, you're trying to solve the opposite of the halting problem, and you can't do that. So if you've got a piece of code that will literally just go on and on and on and on and on forever and never stop, the compiler can't tell that because it would have to solve the halting problem in order to do so. Tangent over, you don't need to know about the halting problem, I just thought it was kind of interesting, so I threw it in there. We're going to train software to understand language. We need to use huge amounts of naturally recurring writing and speech to train language models. So Google is really good at this. You may notice that Google's voice recognition is really good compared to, say, Apple's. And there's a reason for that, and it's because Google has been collecting voice search data for years. So they have a huge library of voice data. Mozilla, which you may know if you browse the web with Firefox, or if you just know of them in general, maybe you use Mozilla Thunderbird to check your email. Not many people do. They are currently bringing together a speech, like a database that you can actually contribute to if you want to. You speak some phrases at it, and it will just store you in the database, because there currently is no large, accurate, proprietary database of voice. And so if you're a new developer who just wants to create a voice learning application, you have to give money to Amazon and to Google straight away to access their database. There's nothing free and open source. So Mozilla is trying to fix that. So if you want to contribute to the cause, then go and search for their little voice database and get your recording in. And it improves the accuracy of everyone's algorithms, which is fantastic. Yeah, NLP, as he said here, could fill an entire Part 2 option. It's a very broad field. So we're looking at computer systems that would be better at assisting humans, and search engines and grammar checks are a big thing. You've obviously used Word at some point to write an essay or whatever, and you know it checks your grammar, it checks your language. So computers are getting better at checking natural languages. Word has been spell checking for quite a long time, but you may have noticed that recently it's got better and better and better. There's a lot of developments that have been around for a long time that now are being strengthened by this artificial intelligence. So you may find that now when you launch Word, it says, hey, do you mind if we collect data and send it back to Microsoft? It's usually because they want to collect data on how you type, what kind of words you use, what order you use them, how you respond to its suggestions. Do you accept that that's a spelling error? Do you ignore it? In what context? Why are you doing that? And it adds more and more training data, because as we'll see in a bit, you need training data to make your algorithms really strong. So the Turing test is an interesting thing. We're going to skip over this, but you may have seen the film The Imitation Game. This is basically, if you've ever had a captcha on a website that says, look at this text and translate it into actual letters, and it's impossible to do, or you've had one of those tick this box to say I'm not a robot, those are captchas. Those are examples of reverse Turing tests. The Turing test is basically a computer tries to pretend it's human. So you hide it away in another room, and you say to a human on the other side of this wall or whatever, you say, there is a human on the other side with like a text messaging application, and you text the computer and it replies back to you. And you have to convince the person that the computer is a human. So how good are computers at being human? There are a couple of bits of AI and robots that have got scarily close to this kind of pretending to be human, but there's still a lot of kind of predetermined programming that goes in. The reverse Turing test is when you're trying to check whether an end user is human or not. So that's the whole I'm not a robot thing, which, believe me, does more than you just ticking a box. It collects a whole bunch of data to check against artificial intelligence algorithms, whether you're a human or you're a robot that's trying to spam their servers. But again, tangent, I'm not going to go into that. So there's a load of criticisms of things and whatnot, but we're not computer scientists, so, well, I am, but we don't really care for the purposes of this. So, yeah, basically, natural language is ambiguous. So that causes a problem for us. So whereas machine code can only be interpreted one way, I would say there are no ambiguous programming languages, but that would be incorrect. But I'm not going to get into that. But yeah, there are some weird things with natural language. So you'll know about this, hopefully, as linguists. You'll probably know more about the grammars and the sort of structure of sentences and whatnot than I do. So I'm not going to go into all of this. This is quite a good example, is spring. What does spring mean? If you ask a program, define what this word means, it will give you back loads of different definitions, because context is really important here. So, there's tons of ambiguity here. So there's different types of ambiguity. I'm going to skip the little quiz at the end. I'm going to skip all of this as well. Yeah, so this covers a lot of what we're going to do anyway. So I'll leave that there. But basically, natural language processing is really cool. It allows us to interpret natural languages with computers, which hopefully you guys see as a useful thing. If you've ever used Siri, I know most people tend to use it to set timers. Like, that's pretty much all I use it for, because it's not very good for beyond a couple of words. More recently, they've done more voice samples, and they've got the voice to sound a little bit more natural, which is interesting. It's a lot better than the old kind of IBM robotic voice type thing, which is not great. Hopefully, you've managed to install NLTK. If not, then please try. So today, I'm basically going to cover the basics. This may be a little bit boring, but hopefully not. I think if you kind of think about what you could use this for, that's the main thing we're going to look at. In later sessions, we'll look at some different topics. So we're going to cover the basics today, but next we'll be looking at WordNet. WordNet is this massive like online dictionary API service that we can use to do a whole bunch of different things. I feel like this background was a bad choice. And then we're going to look at classifiers. So classifiers are more of an artificial intelligence topic, so we're not going to get deep into the nitty-gritty and look at the maths behind them. But classifiers are really useful in natural language, and we're going to build a classifier together. We're going to build a voting classifier, which sounds like it's some sort of amazing thing. It's actually just you take a whole load of classifiers, you get their result, and then you do like what was the modal result across all of them, what was the most common result, and then just go with that. It's just a voting classifier. It basically allows us to kind of brute force our approach to classifiers and be really lazy, so we can just build a classifier that kind of works sort of kind of okay, like 60% of the time, which is pretty good, believe it or not. Then we're going to look at sentiment analysis. I wasn't really sure what to put here, but I thought this like picture of eggs was quite good. So maybe if you're like crack by the end of these sessions, then there's something there. But yeah, we'll be building a Twitter sentiment analysis thingamajiggy. So we'll be able to put in a keyword and monitor sentiment on tweets around that keyword. So when I was testing this, I put in like, I think it was during the election actually. So when I first played about with this, so I put in like Trump and Hillary, and you can see what's the positive and what's the negative sentiment. And I'm not going to get into that debate, but it's very interesting to see the results. So we basically get like a live stream almost of tweets, and we can analyze them on the fly, throw them into our classifier, use our training data to classify them as positive or negative, and then spit back out positive, negative, and we can put that in a graph. And we can go, so for this word in question, what is the sentiment like currently on Twitter? It's negative a lot of the time. Like we have a very depressing internet. Anyway, so the basics. We'll start off with something nice and simple. So one thing that's really important is to be able to tokenize things. So if you've done a little bit of programming before, I'll have to get my whiteboard pens out now. This is where it gets all professional and exciting. If you've done a little bit of programming before, you may have seen, you can split a string up with a delimiter. A delimiter, even. I can never pronounce that word. Doing so well already. So if you've got a massive string, you can turn it into an array. So if you've got this string, for instance, hello, Mr. Smith, how are you doing today? The weather is great, and NLTK is awesome. The sky is kind of blue. You shouldn't eat cardboard. I think that's good advice for all of us. So if we split this into sentences, how could we do this? What kind of algorithm would we come up with? So not thinking about Python in particular, assuming that whatever language we program this in has all the functionality in the world. Well, we could look at punctuation, right? We could say, hey, so there's question mark, there's a full stop. That's probably the end of a sentence. That would be a fair assumption. Assuming the person isn't insane and uses punctuation and perfect grammar all the time, we're not going to get into analyzing tweets and in particular and sort of social media posts where grammar is terrible and you can't tell what is a sentence and what isn't. I mean, human beings, I certainly struggle with that sometimes, let alone a machine which doesn't understand natural languages in the first place. So let's split on maybe a punctuation mark and a space afterwards. So that's all right. Like we've got a question mark here, we've got space afterwards. We've got a full stop here, we've got space afterwards. We've got a full stop here, got space afterwards. Is that a sentence? Hello, Mr. Full stop. Well, it is a sentence, but is in this context that a sentence? No, not really. We wouldn't really agree that that is the main crux of our sentence here, is hello, mister. We'd probably say that this is our sentence, right? So the problem we have is if we take a naive approach and say split sentences by a punctuation mark or by a punctuation mark and a space, then you end up with loads of weird problems. So if we took a naive approach and just said punctuation mark, space, we get hello, mister, we get Smith, comma, how are you doing today, question mark. Then we get the weather is great, comma, and NLTK is awesome, full stop, another sentence. The sky is kind of blue, full stop. You shouldn't eat cardboard, full stop. So that seems to not work. So the reason we use NLTK for this, we want to split our sentence into tokens. So tokens are just literally the individual words or the individual sentences. It's basically a chunk of a sentence. It's a bit of a sentence. So we can split it into sentences. So we got here, one sentence, here's another, here's another, here's another. And NLTK is quite smart and it will do that for us. So it will split it into actual sentences. So it doesn't get caught out by Mr., for example. It will pick up the entire sentence. This is where libraries are really awesome. So I'm not going to get into how that works because fundamentally we don't care. We want to do some cool natural language processing. We want to tokenize stuff. It's going to tokenize this into sentences. We don't care much more than that. That's about it. That is the beauty of a library. It's some code that someone else has wrote. We know how to use it. That's it. We just need to know how to use it. We don't need to know how it works. So we're going to get our sentences here. So we can do sentences equals sent tokenize and then pass this text in. And sent tokenize, you notice, is coming from the library. So we've done from nlt.tokenize, nltk.tokenize, import sent tokenize. What do you reckon sent tokenize does? This might give you a clue. Hello.
Tokenizes the sentence.
Yeah, so we get the sentences out of this body of text. So when we do print sentences on the screen, it will print us this, 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 and this as 4 separate sentences. Then we just do another print just to stick a bit of spacing in here. If you sort of look through these at home, you can copy this and this should run and look all beautiful and fantastic. Then we do this. So we say for S in sentences, so if you remember, we can loop through a list by doing for something in something, and then this S variable becomes each individual sentence. So we're looping through all the sentences in this list of sentences that this has given to us. And then we do print S. So we just print the sentence to the screen. So we're just putting them out on the screen. And then we do this. We can do word tokenize on S. So we tokenize the resulting sentence into words. So now we split every sentence into words. So now we're printing out, hello, Mr. Smith, how are you doing today? That's the print S. And then we have, hello, Mr. Smith, how are you doing today? Now, I believe that the punctuation is separated into its own separate word. If you run it, fantastic. I'm glad someone is running it properly. I was going to do that, but my laptop doesn't seem to be very healthy today. So we've got words, and we're tokenizing the words, and then we print the words to the screen. So we're just printing an array of words. So it's important that we do it in this order. It's not a great idea to start off by tokenizing the words because it can get a little bit confused. So it's a good idea to split it into sentences first. Otherwise, things go a bit strange, a bit wrong. Stop words. So you may have heard, I'm not sure whether stop words is a linguist's term or whether it's just a natural language processing term. If I say anything that you've learned in linguistics or English or whatever you may study, then just sort of look bored and sad at me, and I'll skip over it. So stop words are essentially useless words that really don't change much of the meaning of the sentence. I suppose this is kind of quite a broad definition, and this may be wrong for some languages. So you can actually print these stop words to the screen, and you can see what they're made up of. Let's see whether I can actually get my laptop to play ball. If I can't do it in 5 minutes, then I'm going to give up. So essentially, you've got your stop words, which are things like the, and. No, actually, I don't think and is one. There's a good little list of words that basically don't do much to change the sentence. So in hello, Mr. Smith, I reckon it keeps hello, Mr. Smith, how, I think it gets rid of are just in this sentence. How are you? It might get rid of doing. I think it gets rid of are just in this sentence. If you run it, you might be able to tell me more accurately. So we get rid of the words which don't really change the meaning of the sentence. Because computers, when we're dealing with a lot of data, we like to reduce the resolution of that data because big data is very scary. You may have heard that one of the biggest IT challenges right now is dealing with the huge amounts of data that companies like Facebook and Google and various other people now store. We're creating petabytes of data a day. Our data is growing exponentially. So Google is constantly building new data centers and all sorts of things. Like we are kind of sort of having to grow the amount of storage we're needing bit by bit by bit in order to keep up with this growth of data. The problem with having a lot of data is that it's very difficult to analyze it. So a lot of AI is basically just fancy statistics. And natural language processing is kind of built on top of this, but it's more of an application of artificial intelligence. Yeah, that's what we're in right now. Let's see whether this is going to do something. Is it going to do something? Maybe. Maybe I should be on the right input. That would be a start. If this works, I'll be very pleased. Amazing. So we have our kind of weird Douglas Adams desktop background here. So I hope that works with you guys. So I can actually run some code now. Oh, you don't want to see that. So this is my third year dissertation thingamajig. You really don't want to see me building an operating system. It's not fantastic. So we're going to create a new file. I'm just going to save this. I'm going to save it to my downloads. I have way too much stuff in here. And I'll just call it test. So we got a nice test file. So I can do import NLTK. VS Code is being nice to me. We've got some nice auto-completion here. So I'm going to do nltk.download, like I was saying. And if you run this file, which is not going to be in here, it's going to be in my downloads directory. And then we can do Python 3. So I'm running Linux, so mine may look a little bit weird compared to yours. So don't worry about that. It's just I'm running a different OS. It will be slightly different to what yours looks like. Can you guys see that console at the bottom? Looks a bit small. Is that all right? Okay, I can increase the font size if you need me to. So I've got this here. So you can see mine's all green because I've installed everything. If you click on Corpora, you can actually scroll through and see all the cool stuff that they have built in here. They have so many like random things in there. yeah, there's a lot of cool things, and this is constantly growing. So actually, when I was testing this, I had to re-download everything because everything I had was out of date. And I think currently this hasn't been downloaded, so that's fun. Yeah, it's just updated something, and I think I literally installed this last night. So it's constantly evolving and updating, which is really cool. So I'm just going to get rid of that for the time being. So when we're looking at our stop words, let's do some tokenizing first, actually. Let me just pop this in here. So hopefully this is not going to shout at me about my indentation. No, it all seems okay. No, it's not. So one thing I think I pointed out last time is that Python gets very frustrated if you don't indent your lines properly, which is absolutely amazing if you use literally any other programming language, which doesn't do that. So yeah, you've got to love life on that one. So we've got, hello, Mr. Smith, how are you doing today? The weather is great and NLTK is awesome. The sky is kind of blue. You shouldn't eat cardboard. You've got 4 sentences there, can't count. And then we print out each sentence bit by bit, and you can see it splits everything up. And yes, it does indeed separate our punctuation. So you can see it's just printing out the lists here. Shouldn't goes a little bit wrong here. There are different tokenizers that work in slightly different ways. So we'll have a look at one of those, hopefully in a little bit if we don't completely run out of time. So yeah, that's tokenization. Stop words, we're just going to take one sentence in this example. So this is quite disgusting and horrible to look at. So I'm just going to simplify our printed output just for the time being. So this is all of the stop words for English. So you'll notice that I say, give me a set of stop words in English. So this is my sentence. I tokenize my sentence here, and then I generate a set of stop words. Now, just for the purposes of keeping things simple, a set is basically it's a mathematical term, but we have them in computer science as well. It's basically a load of data in no particular order where there are no repeats. So if you put something into a set, it means that you can't have any duplicates. So you can't have the same stop word more than once, which kind of makes sense. And then we can print the stop words on the screen, so that's what you're seeing here. So there's a lot of kind of quirky, fantastic stop words. So you can all take a little look through there and see what you think. Then we're going to do this. So this I didn't really show last time. This is kind of like a shorthand for building a list in Python. We basically say this filtered list contains W, where W is in this tokenized sentence if it's not, and it's not in stop words. So if that at all makes sense to you, fantastic. If not, it's basically equivalent to starting off a blank array and then saying for W in sentence, so looping through every word in the sentence, and then saying if W isn't in stop words, so if it isn't in our set here, then we append W to our filtered list. So we're just making a list. Python has this really nice shorthand syntax. So if you know Python, great, you'll understand what that means. If you don't know Python, then the other one is a little bit easier to understand. Write your code however is easiest to understand, not how, don't write it as concise as it should be. Write comments on it, write what's easy for you to understand, because we do want you to be able to understand your own code. There is a rule in programming which is basically write code that is about half your brain's capacity to write. Write simple code, because code is twice as difficult to debug as it is to write in the first place. So if you write code that is literally the top of your mental ability to write, and then it breaks, you have to think that you're using double that mental ability to then debug it when it's broken. So don't do that. If you don't understand it, don't write it. And if you're doing a piece of coursework in code, that's also called plagiarism. So just don't do it. And then we print filtered on the screen. So I'm going to stop printing the stop words so that it's not as confusing. So we can see, hello, Mr. Smith, today. So apparently this sentence now makes no sense thanks to our stop words being removed. Stop words can be quite useful to take out of sentences, but sometimes they're a little bit kind of useful. Like I say, natural language processing is not a fantastic, accurate art. We can use a different sentence, so we'll see if this does something. We can say the sky is kind of blue. Let's see what that does. So, got the sky kind of blue. That kind of works a lot better. So we got the meaning of the sentence. Let's see what you shouldn't eat cardboard nets us. Again, very important advice. So, yeah, we've kind of cut down. So we got rid of the should because it's basically saying not eat cardboard. You not eat cardboard. It's instructing you to not eat cardboard. So that still kind of makes sense. But yeah, don't rely on stop words to be super, super accurate because it's not an exact science. There is still active research over kind of what should be a stop word, what shouldn't be, and using them in general. So don't kind of rely on that. So the next thing to look at, is it going to dual source me? How exciting. Stop words. Oh, it's on both screens as well. It's like split across. This is really high tech here. I'm glad I paid for this. Stop words, all well and good. Stemming is kind of important. So stemming is where we get the stem of the word. The semantic meaning often relates to the stem of the word. So again, all this stuff is kind of about cleaning up our data, because when we're dealing with big data sets, we want to kind of get rid of outliers, we want to kind of deal with things, and in natural language processing, we're looking to get the bits of the sentence that show us the meaning. We don't really care about a lot of extra stuff. So here we've got some code that allows us to do stemming, conscious of the fact that I need to do that again because otherwise I can't see what I'm doing. So I'm just going to get rid of this and replace this with the stemming code. So what do we think this is going to do? Yep.
Turn all the words into their stems.
Yeah. So what will our output most likely be? That would make sense, I reckon. It's not quite that, because there is a quirk to this. So we have walk, walk. Oh no, we have a walker. Okay, that's exciting. So we have walk, walker, walking, which goes to walk, walk, and then walk-ly gets turned into walk-ly with an I, which is an interesting quirk. We also have a different stemming algorithm. So alongside this Porter stemmer, which is kind of like, I think this is the most widely used. I think it was invented in MIT or Stanford. I can't quite remember. So we're importing from NLTK.stem. We import Porter stemmer and Lancaster stemmer. And then we're just saying PS is equal to Porter stemmer. and then ls is equal to Lancaster stemma. And then we just give it an array of words. We've got some endings on them. And then we say, for every word in this words list, print the word and then stem the word. So the top one, this example, was using the Porter stemma, and now we're going to look at using the Lancaster stemma. So if I run this, the Lancaster stemma seems to be doing a better job. So it may interest you to know that the Lancaster stemma is named the Lancaster stemma because it was invented at Lancaster University in the UK. How exciting. Ooh, you're so engaged. I love it. So yeah, the Lancaster stemma does pretty well as well for us. So there's different stemming algorithms, and there's lots of kind of theory in natural language processing as to how these work and why they work like they are. But essentially, we want to get the stems of the words, so this can be really useful for that. And we can kind of mix and match things. So if I grab my thing from before, I just pop that in there. I'm going to have to clean this up a little bit. So I'm basically just merging this code, the 2 bits of code together. So again, from last time, I've got the "Hello, Mr. Smith, how are you doing today?" sentence. I've got the tokenized sentence here. So that will get me an array, a list out of this sentence. So you've got "Hello, Mr. Smith, how are you doing today?" in our list. We get the stop words again. I'm not going to print the stop words on the screen because we know what they are. Then we're going to make a filtered list, just like before. We filter out the stop words. We print the filtered list. And then we can say for W in filtered, we can run that on there, see what it does. Fantastic. So we do some interesting quirks to this stemma that we are now learning about. Let's see what the Porter stemma does. So yeah, there's a lot of kind of simplification. So one thing you'll see that stemming does as well is it makes things lowercase, because generally when you're dealing with text in a computer, so a really, really simple example is like a text adventure game. If anyone's ever played something like Zork, the text adventure, it basically says, like it pops up on the screen, you are in a room, you see a door and you see a scary hellhole. Do you go to the door or the scary hellhole? And you go, like press B for the scary hellhole, you type in B, press enter, and it goes, you press B, so you're going in the scary hellhole, you die, how sad. You know, like that's basic text processing. But what if you put a capital letter B, a lowercase letter b, something that isn't B? Generally, you'll normalize the text input, so you'll make it all lowercase, because it's just easier to deal with it all in one case. Because the way that characters are encoded in a computer, S and capital S are very far away from each other on the spectrum of character encoding. I'm not going to get into the details there, but yes, you know, if you want to look up Unicode and how amazing that is, then I won't stop you. Interestingly, emojis are part of the Unicode standard, so if you like using emojis, thank Unicode. It was originally a Japanese thing that came from Japan, which is why you have things like sushi rolls and whatnot. That was like the early emoji, and then it kind of migrated, so now you've got even more stuff, and now we've decided we want skin colors, and so as a result, there's all these skin color variations that they tack on the end of emojis. But yeah, that's quite cool. I remember that back in the day, trying to explain to my dad that an emoji was text and not an image, so it wouldn't use up all his data. That's an interesting conversation to have. Yeah, hopefully you guys know that. I'm not going to explain that. It's a bit beyond the scope of this talk. So that's all about stemming. So these, I'm kind of just giving you tools here, so we'll be using them in later sessions, but these are kind of the basics to cover. And so stemming, super important, really useful tool. So we got part of speech tagging, and I think this and maybe the next slide, we might leave it there. So part of speech tagging involves tagging parts of speech. We're really good at naming stuff in computer science. Like we're so creative. So these are all the parts of speech you can tag. Now I will be honest in saying that I have completely stolen this list from a list on NLTK's website. I do not know all of these things. I just know they exist. You guys, as the linguists, the English students, will probably know a lot more about all these different things than I do. I kind of just hack code together and hope it works. So yeah, we can produce some really interesting sentences. There's lots of weird, like extra kind of edge cases that we can use. So yeah, there are lots of parts of speech to tag. So we're looking at the NLTK corpus here. We can grab the State of the Union corpus, which has got some really awesome data from. Hopefully we'll be able to produce something which looks quite cool by using this part of speech tagging. So essentially, we can break up a sentence and parse it into various components. So the kind of very simple thing is you've got something like the doctor shoots the Dalek. So in that sentence, you've got kind of like, first of all, you've got the biggest thing. We'll call it S. S is for sentence. Again, you know, we're very creative at naming things. The sentence is called a sentence. Who would have thought that? So now I'm going to switch colors because I like to be creative. So we have the article in the sentence. I think the main thing we can refer to is we've got a noun-verb phrase in this sentence. And again, I'm mainly talking about how you split a sentence up. So if my linguistics is horrible here, please be kind. So we can say the doctor shoots is a noun-verb phrase in this really simplistic grammar. And then we can say that we've got like the article, so the in this case, on either end, we've got our article, and we've got our nouns. So we've got doctor as a noun, we've got shoots as a verb, Dalek is a noun. So you can see that we can break this sentence up. So we can break it up from sentence into a noun-verb phrase, and a noun phrase. So in this context, in this very, very simplistic grammar, which doesn't follow the rules of English, we can only use these words that you can see on the screen. We've got the Dalek, the doctor shoots is our phrase, and it all comes together to make this sentence. So it's quite important that we can tag parts of speech. So that we can start to analyze our sentences. So here I'm going to switch back to this thing again. Fantastic. And so we're going to do some part of speech tagging, and hopefully this will result in some cool output. So just a little side note, I didn't cover exception handling in the last talk. So basically, try and catch kind of are exactly what they mean in English. Try means try to do this. Catch means if this particular error occurs, deal with it like this. In this case, I'm just telling the person who's running this code the error has happened, and there is no error handling whatsoever. Hello. Yeah, I can do. If I can actually remember how to change the font size on here. Oh, is it? Ah, fantastic. Can you see that? Is that all right? Okay. Okay. So I'm just going to make this a lot simpler by just bringing that out of here and getting rid of that function, getting rid of this down here. So I put this in a function, but it doesn't really have to be in a function. It's just a way we can kind of abstract away and hide it to one side. So we've got import NLTK from NLTK.corpus, import state_union. This gets us all the state of the union addresses ever given. So this is a really cool data set to play with. And then we're importing punct sentence tokenizer, which when I first saw it sounded like some sort of like rap group that raps about natural language processing, I guess. It's quite sad. But no, what our sentence tokenizer does here, I believe, is does some slightly better handling of our punctuation, if it's going to work. Yeah, so our punct sentence tokenizer, I believe, gets rid of our punctuation, or it does something to our punctuation. Yeah, so the point is that there aren't just the simple sent and word tokenizers. There's all sorts of different ones, but they all follow a same kind of interface, which is you just give it some text, and then you run this tokenizer on it, and then you get this, you get a result. So what we can actually do with this is we can train the sent tokenizer with some training data. So we're training it on the 2005 George W. Bush State of the Union address, and then we're actually going to run it on the sample text, which you can see is the 2006 George W. Bush State of the Union address. So stateunion.raw, you just give it a file name. There's all these file names, like you can read them in raw text if you want to. But the .raw just means we import the raw data, so it's not tokenized, it's not tagged or anything. Like you can import tagged things, which can be quite useful later on. But for now, we're just importing the raw text data. So this is just like a fancier version of our string from before, our massive string. So we're saying punct sentence tokenizer, train it, and then tokenize on this sample text, which is just the 2006 George W. Bush State of the Union address. And then we're saying for I in tokenized, so for every word in the tokenized list, you could do for W in tokenized. Doesn't really make much of a difference. Let's do W because it's word. So for W in tokenized, words is equal to NLTK.word tokenize W. So we've split our sentences up, and now we're splitting our words up. And then we can do some tagging. And we got NLTK.pos tag, and pos is part of speech. And you can see in VS Code, it's been very nice to me. It's given me an example. So I can see that pos tag and word tokenize for John's big idea isn't all that bad. It tells me that I've got a noun phrase, I've got a noun, I've got a verb, I think, or an adverb, something. So we've got lots of different parts of speech here, right? I think JJ is an adjective, even. So I can look at my handy-dandy reference. Yes, JJ is an adjective. So you can see that we've got the entire George Bush State of the Union address here, and we've done some part of speech tagging. So we can see this kind of really cool, like, splitting up of everything. So you can see you've got bench, the, law, and we got all these different parts of speech tagged. So we're starting to actually process language properly. So we're starting to actually break things down. and break things into chunks, so the computer can actually start to apply some logic to this. Hopefully that makes sense. Okay. So I think that I'm gonna kind of leave it there. So if you go over part of speech tagging, we'll try and get these slides up. If you go over part of speech tagging a little bit and just see what you can do with it, we're going to look at chunking, chinking, which I promise is not some kind of like racist thing. That's what I thought it was when I first heard about it. It sounds very dicey. It's not at all. So there's chunking, there's chinking, and then there's named entity recognition, which we're going to look at. And we can see the different entities recognized. And we'll be showing kind of like a breakdown of a sentence into a parse tree for different entities. So you can see that NLTK can do this recognition of different entities in a sentence. It's similar to part of speech tagging, so we'll come back to that next time. I think that's it. Thank you very much. If anyone wants to take a picture of that, you're more than welcome to, if you really want to know everything.